Last time we talked about the p-adic absolute value on the rational numbers, q. So if you have a rational number, x, and you have a prime p, then you write in the form p to the alpha times a over b, and p to the minus alpha is, by definition, the p-adic absolute value of x. And in this video, we're going to look at some properties of the p-adic absolute value. And we'll see that it has properties that are a lot like the regular absolute value. So first of all, one of them that's immediate from the definition, so property 1, is that the p-adic absolute value of a rational number is greater than or equal to 0. That follows from the definition, and that the p-adic absolute value is 0 if and only if x is equal to 0. So number 1 follows immediately from the definition of p-adic absolute value. The second one is that for any two rational numbers x and y, the p-adic absolute value of the product is the product of the p-adic absolute values. Just like for real numbers, the absolute value of a real number. So the proof of this is straightforward. I mean, if you just write x as p to the alpha times a over b, where p doesn't divide a or b, and then y is, say, p to the beta, a prime over b prime, where p doesn't divide a prime or b prime, then xy is just going to be p to the alpha plus beta times a prime over b prime, and p doesn't divide a prime or b prime, and so the p-adic absolute value is just equal to negative alpha, negative parentheses, alpha plus beta. This is equal to negative alpha minus beta, which is the absolute value of p, the absolute value of x times the absolute value of y. So that's the proof. And now here it was actually quite essential that p is prime, because that implies that p doesn't divide anything in here, a prime over b prime. All right, the next property is the triangle inequality. So the triangle inequality says the absolute value of sum is less than or equal to the sum of the absolute values. And this is certainly true for the absolute value of real numbers, but for the p-adic absolute value, we can actually say something stronger. So in fact, it's not just that the sum, that the absolute value of the sum is less than or equal to the sum, it's actually less than or equal to the maximum of the absolute values. All right, so this one, the proof is less easy to see. And actually, we'll prove a lemma first. So first, we'll prove that if the p-adic absolute value of x is less than or equal to 1, that implies that the p-adic absolute value of 1 plus x is less than or equal to 1. All right, why is this true? Well, first of all, if x is 0, it's clear, right? Then well, the p-adic absolute value of x is just 0. Not 0. Yeah, it is 0, right, by definition. And then you just get the p-adic absolute value of 1 plus x is just the p-adic absolute value of 1, which is equal to 1. Okay. Sorry, it's equal to, let's see. Yeah, it's equal to 1. Okay. Which is certainly less than or equal to 1. All right, so suppose that x is not 0, Well, you can write it in the form C over D with C and D co-prime. So GCD of C and D is 1, and P not dividing D. Okay, the reason for that is because the p-adic absolute value of x is less than or equal to 1. So if that is the case, that means that it must be like 1, 0, p to the minus 2, p to the minus 3, etc. And so in particular, you can write it, when you write it as a fraction, D will not have, by dividing out by powers of P, you can assume that P does not divide D. Okay, so we write this, then 1 plus x, well, is 1 plus C over D, and that's just C plus D over D. Now, since P does not divide D, we see that the p-adic absolute value of 1 plus x is less than or equal to 1. So that proves this result. Now, how does this result prove the fact that we want to prove about the p-adic absolute value? Well, so going back to the statement we're trying to prove, which is this, not this statement, we're trying to prove this statement. So to prove this statement, if y is equal to 0, then certainly the p-adic absolute value of x plus y is just the p-adic absolute value of x, which is less than or equal to the maximum. Now, if y is not equal to 0, then we can assume, without loss of generality, that the p-adic absolute value of x is less than or equal to the absolute value of y. Right? This is clear. We can assume this without loss of generality. Then the p-adic absolute value of x over y is less than or equal to 1. So, okay, we see that just by dividing both sides by the absolute value. And then we're using the multiplicative property, the absolute value. And so, by the lemma that we proved, the p-adic absolute value of 1 plus x over y is less than or equal to 1. Which implies, just by combining the fractions and using the property of p-adic absolute value, that the p-adic absolute value of x plus y is less than or equal to the p-adic value of x, which is, of y, which is the maximum. And that proves the result. So we see that the p-adic absolute value satisfies the properties of an ordinary absolute value, the absolute value of a real number. So we have, let's see if I can highlight this. We have this, but we also have this stronger statement, stronger version of the triangle inequality. So this is something that's special to the p-adic absolute value.